Okay, so we're going to talk a little bit more about the Ekman layer and this Ekman force balance that we were talking about, because now we're going to add in the hydrostatic balance as well. And the reason why we want the hydrostatic balance is because it's going to allow us to put the pressure consequences of these convergences and divergences that might be driven by the Ekman flow. Upwelling, downwelling, Ekman suction, Ekman pumping, all of this stuff has pressure consequences that we're going to start to think of through the hydrostatic balance. And that's going to help us link the pressure field to the flows that we want to talk about next that are driven by pressure. Okay, review our balances again. Hydrostatic balance balances the vertical pressure gradient to the combination of the centrifugal force and gravity. Taylor-Proudman theorem involves three different terms in the momentum equation, and remember, it's the one that tells us that there's no shear, and so in the rapidly rotating with negligible friction, negligible density, the rotation axis direction is not. There's no tilting in that direction. Everything moves around in the column in that direction. The Ekman layer is the one we talked about last time. That's the Coriolis force balanced against the friction force, or the turbulence parameterization of the friction of the turbulence. Either way, but this one gives you an anomaly only in that surface, and also actually in a deep bottom boundary layer, but only a boundary layer impact where you deviate from those Taylor-Proudman columns or whatever else is going on with a little shear in the Ekman layer, and that shear, if the viscosity here is constant, gives you a nice spiraling pattern, which is what Ekman solved for. But if that viscosity is not constant, then you just have a simpler force balance where there's motion to the right of the wind in the northern hemisphere, to the left of the wind in the southern hemisphere, and we don't really know what it looks like as a spiraling pattern or whatever. It's something more complicated in the boundary layer, but we know that for the forces to balance, we integrate over that whole layer. It's on average to the right of the wind in the northern hemisphere, to the left of the wind in the southern hemisphere. And inertial oscillations are kind of interestingly similar to the Ekman layer in that they involve the Coriolis force and one other term, but instead of friction in Coriolis, it's the acceleration and the Coriolis. So it turns out you can actually put those two together in a nice way, which we'll talk a little bit about today. Okay, so we quickly went through non-dimensionalization last time, but I'm going to go a little bit more carefully through non-dimensionalization because this may not be familiar to all of you. So the way that so why do we even want to do non-dimensionalization of the equations of motion? What we want to do is we want to see how big the different terms in the equation are. And to do that, we estimate the size of the motion we're thinking about. What's its typical time scale? What's its typical length scale? Velocity scale? Depth scale? So on. Figure out how all the different terms in the equation scale with these parameters. Both of these are pretty approximate, but all we're really trying to do is to get a scale of the different terms. And then we collect together all the dimensional pieces into dimensionless quantities. We already have seen a few examples of this: Rossby number, Ekman number. And when we've done that, we then can see how different terms in the equation relate in size to each other. So here are some examples of dimensionless parameters that you might find in this process. The Reynolds number gives us the advection of momentum versus the viscous term. Let's go back and see. That's this term versus this term. Okay. The Rossby number gives us the momentum advection versus the Coriolis force. That's this term versus this term. The temporal Rossby number gives us the momentum tendency versus the Coriolis. That's this term versus this term. 1 over f times time scale. So if you divide this term by that term, this term by this term, the f times time scale is in the denominator, and the size of this velocity and the size of this velocity are pretty similar, so those just cancel out. So you get 1 over f times whatever the time scale is. And we're normally converting between a derivative and just a delta v over delta t, that is an increment in velocity over an increment in time, or a typical velocity difference scale versus a typical time scale difference in time. That's what we mean by these typical T, L, U. It's not really the velocity necessarily. It might be the difference in velocity from place to place over a certain time scale T, over a certain length scale L, over a certain depth scale H, and so on. Okay, and then the last one, we talked about it last time, the Ekman number. We talked about it, and it's the viscosity over the Coriolis force, and we said the Ekman number is going to be order 1 in order to have an Ekman layer where the viscous term and the Coriolis term could balance. So, let's look at this again. Here's the full momentum equation with no approximations made. Here's the Taylor-Proudman theorem, which now we have an Ekman number that's small. We have a Rossby number that's small. We have a temporal Rossby number that's small. So that means this term is small, this term is small, this term is small. This term is not even part of this, these numbers that we just talked about, but this is the one that has to do with the changes from place to place in density. So cancel that one out, and then what we've got left is the Taylor-Proudman theorem. Inertial oscillations have the advective Rossby number small, so this term is small. The temporal Rossby number is order 1, because this is just as big as this. That's the balance we're actually going to find. The Ekman number is small, which means that friction is negligible. And we don't say anything about the pressure and the gravity in this case, but we don't think in an inertial oscillation you wouldn't want those to be conspiring in such a way as to make this anomaly go away. But as we saw in the lab experiment where we had Taylor columns sliding around and just wobbling like inertial oscillations, we could think of the inertial oscillation solution here as being an anomaly to whatever the velocity was governed by all the rest of the equations conspiring together. So because this term depends on only one velocity, this term depends on only one velocity, as they're both linear in velocity, we can superimpose an inertial oscillation on a solution of the other terms in the equation if we're careful about this nonlinear term. That one can screw up that kind of simple idea. Similarly, the Ekman layer involves two terms that are linear in velocity, so you could add it on and get just the Ekman layer shear in that little layer that goes on top of a Taylor-Proudman column or whatever else. The hydrostatic balance is the vertical direction, something slightly different from the other things that we've normally talked about, but that's helpful. Okay, here's our force diagram. Here's our Ekman layer. Ekman layer is near the surface. It has a sheared pattern with some kind of turbulence, frictional effect that's important. That's coming from the wind. The stress is setting the boundary condition for that frictional term. And then when we get deeper, that friction has disappeared, that turbulence has disappeared, and we converge to the interior flow. The simple force diagram is like this, with the wind balanced by the Coriolis force, which means that on average, the Ekman transport has to be in this direction, to the right of the wind in the northern hemisphere. And we talked a little bit about the molecular viscosity last time. It's actually, you can go into a lot more complicated detail and think about this as a divergence of a viscous flux of energy, of momentum, not of energy. This helps you maybe think about the way that the surface wind provides a flux of momentum into the surface, and that flux is getting transferred down and down and down through the Ekman spiral. If there was any divergence in that flux, that would tend to accelerate the layer. And the divergence of this flux, if the viscosity is constant, is just the same old friction term that we've been seeing. And that says, as like we talked about last time, it's an anomaly from its neighbors, this kind of second derivative. Sorry, this is the complicated horizontal form. We were looking at it with the ddz squared form. But if you wrote out the finite difference form of a Laplacian, you see that it really is just the anomaly, the deviation from the average of its neighbors. Now, why in the Ekman layer do we care more about the vertical derivatives than the horizontal derivatives? And why it was we were replacing this friction law with ddz squared rather than ddx squared plus ddy squared plus ddz squared of v is because the ddz squared tends to be a lot bigger in the Ekman layer because the motion tends to be uniform in the horizontal and then strongly sheared in the vertical. Just like we've been thinking about these large aspect rates, thin aspect ratio layers. If you want to get fancy and think about this in terms of the Reynolds stresses, you can think about the divergence of this viscous flux as actually being a divergence of an eddy flux, a Reynolds eddy flux. If you haven't seen Reynolds stresses, this probably doesn't mean anything to you, but this is the way that we might extend this mathematically and make a relationship between this viscosity and the turbulence itself in the layer and the stresses that are related. Okay. So now let's go back to scaling this momentum equation, thinking a little bit about how we talked about doing this scaling, estimating the different sizes. Okay, how big is this term? Well, this is a velocity scale over a time scale, at least in the first part of it. And the second part, it's v dot grad v of v dot grad v, so it's a 2 velocity squared over a length scale. Both of those, compared to this term, give you the 2 Rossby numbers. So when we drop this term in favor of this one, it's because that Rossby number, let's go back and look at what our Rossby number is. Rossby number u over FL and 1 over FT are both small, which means that this term is small in comparison to this term. That's how we made this substitution. The horizontal pressure gradient term here, we're just neglecting it. It's not because it's gone, it's just because we're thinking about the anomaly within that Ekman layer. And then when we try and contemplate a balance for this perturbation velocity due just to the viscous term, that is this balances this, these guys, if that balances that, that means that the Ekman number, which is the size of this term versus the size of this term, needs to be 1, so that this is just as big as that, and they can balance each other. And that's how we get the Ekman depth, is from that balance. And this is the Ekman. This conception results in the Ekman transport, which is the vertical integral of the horizontal Ekman velocities, which goes like tau over rho times f. So this quantity is something that we estimate in the homework. This quantity is something that we estimate for this paper. That's the whole deal. This guy is what we're thinking about. In the southern hemisphere, you use the same form, but f is now negative, so you get motion to the left of the wind rather than to the right of the wind. And we talked about how this, in the equatorial case and in the coastal case, leads to upwelling. But let's think a little bit more about this Ekman pumping and suction mechanism. How is that going to work in the real world? Like, when do we tend to have gradients in the winds? Well, we talked a little bit about the trade winds, that is the winds that are right at the equator that head from east to west. It turns out that if we go a little bit farther north, a little bit farther south, we enter into the westerlies, which are coming from the west to the east. So in between the equator and those westerlies, there is a gradient, something like this, that is occurring in the wind. So let's take a look at how that works. This is a map with a very coarse representation of a very old-fashioned wind stress map, but it's nice because the arrows are nice and big, so you can see the mean wind direction here in the Southern Ocean tends to go from west to east. And here at the equator, it tends to go from east to west. And here in the northern hemisphere, around 40, it goes from west to east. And there's a little bit going this way, around 60, going a little bit backwards, maybe not so obvious over here. All right, let's simplify this. Big red arrows going that way, big red arrows going that way. Roughly this large-scale pattern of the trade winds next to the westerlies in both hemispheres. Okay, what's the Ekman transport associated with this? Well, this arrow is in the northern hemisphere, so it's going to have an Ekman transport to its right, going this way. This arrow is in both hemispheres, both just north of the equator and just south of the equator. So in the northern side, it's going to have a northward transport as its Ekman transport, and the southern hemisphere side is going to have a southward Ekman transport. Same for here, 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 here. We get something like this. So now here the Ekman transports are the little purple arrows that are there because of the winds that are the red arrows. Well, hey, that's just some of the circumstances like this. There's some convergences implied by that, and maybe divergences too. Let's go back and look. There should be a convergence here because these winds are making an Ekman transport that's equatorward, and these are making one that's poleward. Poleward, equatorward, convergence. Poleward, equatorward, poleward, equatorward, divergence, convergence. And then on this side, we're actually seeing a divergence going the other way. This might be reminiscent to something you might have considered by looking at the Collins book. If the winds were going around in a cyclone, which happens in every big storm is a cyclonic wind anomaly, then the Ekman transport would be out of the cyclonic wind region. Whereas if you had an anticyclonic wind, a high pressure system, like happens on very dry, clear days, then the Ekman transport in the ocean would be inward everywhere. And so this cyclonic wind pattern would tend to have a surface divergence and upwelling traveling along with the storm. And this anticyclonic wind pattern would tend to have a surface convergence and downwelling underneath it. Interesting. Does that have anything to do with these? Yes, it does. We know that there are these small scale upwelling signatures, but are these bigger features also Ekman upwelling and downwelling and that kind of thing? Well, let's go back a little bit and think about how convergences and pressures and upwelling and downwellings work through the hydrostatic balance. Here's our hydrostatic balance, which is true when the aspect ratio is small. And we have talked about this a little bit. So this is d pressure dz, because this gravity plus centrifugal force is only in the z direction. We add those two, balance those two together, bring the rho over to that side. dp dz equals minus rho g. That's the balance of these two terms. If we integrate this, that's what gave us the formula of the weight above you per unit area is what gives you the pressure. And the pressure at the surface is 0, or atmospheric pressure, but that might as well be 0 because that's not very much pressure from the perspective of the ocean dynamics. Or you could set it to a constant if you want, or you could get worried about the atmospheric pressure variations, which actually do an important stuff, but we'll talk about that later. Things like storm surge can be driven by atmospheric pressure variations. But anyway, here's the pressure, the weight above you per unit area. So this is where we got to this weight above you per unit area with the tall stack of pillows, short stack of bricks. Tall stack of pillows, they both would have medium pressure because there's more stuff, but it's less dense, versus less height, more dense. So when we look at this formula, it's the integral of the density, dz, from the top to the depth, from the surface to the depth that you're at. So in this case, this would be high pressure underneath bricks, which have high density, versus a stack of pillows the same size, same height, would have low pressure because the density is small. So this integral, if the density is big, ends up being a lot of pressure, lots of weight above you. If the density is small, it ends up being not so much pressure because there's not so much weight above you for the same interval. But if you have tall and short, then now you're not only putting different densities inside this budget, but you're actually changing where z naught happens. It's either higher up or lower down. You're changing the sea surface height. So underneath a sea surface high, you'd expect to have high pressure, and and sea surface low, you'd expect to have low pressure and high pressure and low pressure, like this. Even if the density is constant, this fluid looks like it's is meant to indicate a relatively constant fluid. Then the weight above you per unit area would say the hydrostatic pressure would be related to the sea surface height. Sometimes this is called a geopotential height anomaly, where it's the height of a geopotential surface goes up and down and up and down and up and down, which makes a pressure field below it. Okay, but we could put those two together and then have a medium pressure underneath a tall, low density stack, which weighs the same as a short and dense stack. Okay. And we talked about this in terms of the pycnocline and halocline and all that from before, that the pycnocline is really the change in density at these intermediate depths. So the pycnocline going up and down means you've either got a lot of light stuff, the light stuff being the surface layer above the pycnocline, or a bunch of dense stuff from this deep zone getting lifted upward. That's how we got bricks down here, we got pillows up here. So changing depths of the pycnocline is changing the transition point between pillows on top and bricks at the bottom. So if we have a sea surface height, well, something like this, in the middle of a big pressure anomaly like this, then in this surface layer we would have high pressure because we have pillows stacked higher than here than here. So see, this pillows start higher than this or this, so this, if we take the pressure right here, we expect this has high pressure, this has low pressure, this has low pressure compared to this. But now, if the pycnocline is depressed underneath, now we get down here and we're looking at the bottom of the stack of pillows and it's being balanced by bricks on both sides. So the bricks on both sides, from this deeper, denser water being relatively high, because the pycnocline here is relatively shallow, that means that when we get down here, we might have the same pressure under these three stacks. Because here we've got a medium-sized stack of pillows and a medium-sized stack of bricks. Here we've got a tall stack of pillows and a short stack of bricks. Medium, medium. Down at the bottom, it might actually have no pressure gradients among those locations. And in fact, if we look at the pressure field, we've talked about this before. This is the pressure field at 5 meters of depth. There are places where there are high pressure, these green regions, and there are places where there's low pressure. There's not a whole lot of density difference in the surface. I mean, there can be some differences in the surface layer, but really, this is 2 meters worth of sea surface, or 4 meters worth of sea surface height variability at only 5 meters depth. You're not going to change the density enough. The density doesn't change by 40% enough to change that over that kind of a short distance. But you can have the sea surface height actually start higher when compared to the geoid. If it starts high, sea surface high, you're going to have higher pressure at 5 meters from the geoid. 5 meters below the geoid, which is what we're really talking about when we say 5 meters depth on average. We mean 5 meters below the equipotential surface where the oceans would be if they were not moving and if there weren't any pressure anomalies. So these areas seem to be a meter or two above the typical. These areas in dark blue seem to be a meter or two below the typical. What if we go deeper down below the pycnocline? Then we don't see hardly any pressure gradients in the horizontal out here in the tropical and mid-latitude regions, but down here under the in the Southern Ocean there is still a pressure anomaly from high on the equatorial side to low on the polar side, and that is preserved all the way down. Okay, so now we've covered how the pressure field looks in the real world, or I guess a model of the real world is what this is showing. What is there a relationship between those convergences and divergences and high pressures and low pressures? Let's see. Here's the Ekman, here's the mean winds again. Here's the even simpler mean winds in the red arrows. Here's the Ekman transports, which implies that there are convergences everywhere where we see a C, C, C. Divergences everywhere where we see a D, D, D. And if the water converges, we would expect it to pile up at the surface and maybe depress the picnic line down, remembering that that convergence is happening in the surface layer, because the Ekman is only a surface transport process, not a whole depth process. So it's going to lift up the surface and push down the picnic line. Or if you have a divergence, it's going to depress the surface and suck up the picnic line from below. Which means that we would expect to have, within the surface layer, everywhere there's a convergence, we would expect to have high pressure from the sea surface height. Everywhere where there is a divergence, we would expect to have low pressure from the sea surface depression. And that's exactly what we see. In these regions, these subtropical regions, high, 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 look, subtropical regions, high pressure. Divergent regions, low, 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 low. High pressure in the regions where the Ekman transport converges, low pressure in the regions where the Ekman transport diverges. What if we go deeper? All of those pressure gradients, except for this one, underneath the Antarctic circumpolar current, which actually goes to deep, deep, deep depths, have disappeared. How do they disappear? Well, everywhere where there's a sea surface high, there must be a tall stack of pillows there, which means that the picnic line must be depressed underneath all the highs. And everywhere where there is a low, in order to reduce the magnitude of that low when we get down below the picnic line, it means that the picnic line had to be elevated underneath the sea surface low in such a way to have a stack of bricks start to compensate for the tall stack of pillows that are underneath these high pressures. So now we come back to this figure and we see that this actually is one of these subtropical anomalies in schematic. Here's the sea surface high, here's the tall stack of pillows, there's the picnic line being depressed underneath it, and to the west side there's a smaller stack of picnic line elevation, to the east side, small stack of pillows, picnic line elevation. That is the basic gist of how the Ekman convergences and divergences lead to high and low pressure anomalies within the surface layers, and then the picnic line depressions underneath lead to the surface pressure anomaly being canceled out and relatively uniform by the time we get below the picnic line. All right. That's it for us tonight.